This is a unit that has some pretty in-depth topics that are not typical, not like the other units that we've studied this year. So my strong recommendation would be that you make sure you pay attention to the Edpuzzles and the reading and the other ancillary materials that prepare you for this. So a couple things we're going to take a look at. First of all, um, there is a wave-particle duality of light. In the last unit, Wave, Sound, and Light, we looked at several um, phenomena that demonstrated that light does indeed travel as a wave. Those include interference, especially the Young's double-slit diffraction pattern, where you have both constructive and, more importantly, destructive interference. The fact that we can polarize light means that light comes in certain orientations of waves. And then Doppler shift, the fact that we can get different colors of light coming to us because of its relative motion is a result of the different wavelengths as the wavelengths shift as it moves towards or away. What we're going to learn in this unit is we're also going to have some particle nature of light. So we're going to experience through this unit what different things give us evidence that it sometimes exhibit particle-like properties. So I'm not going to give you those, but we're going to talk about that a little bit later. So one of the most pivotal experiments in this was the black body radiation, or the ultraviolet catastrophe. So part of what this is sorry, an object emits electromagnetic radiation depending on its temperature. So if I have an object that's radiating this temperature, 5800 K, it radiates a little bit of ultraviolet, or a little bit of violet, a little bit of ultraviolet, a little bit of Roy G. Biv, and then down it radiates into the infrared region as well. And this is the temperature of the sun. So the peak intensity that comes from the sun is this yellowish greenish color. If I decrease the temperature of the emitting body, not only does the intensity decrease, I get a shift of the peak intensity. So over here on a light bulb, the peak intensity is more of a yellow orange than it was the yellow green. And if I furthermore bring it down here, the peak intensity is red, or even into the infrared range. So and I can, of course, increase my scale here to showcase where the peak actually is. So, again, let me decrease my scale. With higher temperatures, it shifts towards the violet end. With lower temperature, it shifts towards the red end. So this is a pretty valuable model, but I'm going to go back and talk a little bit more about why that's important later. It's not, the importance here is not just that the intensity increases, but the peak intensity shifts from a different color, shifts to a different color or a different wavelength. But we're going to come back and revisit this later in the notes. So let's frame this with a little atomic history. The word atom is actually Greek. It meant indivisible. So at one point we thought that the atom was the smallest piece of matter. In fact, it was indivisible. We've come to find out that, of course, is not the case. So in 1897, J.J. Thomson did some work, and he said, hey, there's different parts of the atom. It is divisible. There's some negative pieces in it. There's some positive pieces in it. And he developed what he called the plum pudding model. So there's a big blob of substance with these little negative electrons inside, distributed throughout the atom. Come to find out this is incorrect. Rutherford shortly after found out that the atom had a concentrated nucleus. So the way he did this is he put a source of alpha particles that were shot at a thinly pounded gold foil. So he tried to make this only a few molecules thick, or a few atoms thick. Of course, it's going to be still within the hundreds of molecules thick in some place. But even with that, the particles that were shot at the gold foil mostly went straight through undeflected and hit this. So even though it was going through a thinly pounded piece of foil, it didn't hit anything because there was so much space between those molecules. So every once in a while, some of those particles bounced back this way, or bounced back this way, or got deflected slightly, but most of the particles went straight through. So again, he determined that most of the atom is indeed empty space. So that was the gold foil experiment. And so what he said is there's a concentrated nucleus and then empty space around it. So continuing on, we found out that Bohr developed, not only is there a concentrated nucleus, there's these orbitals that circle. There's orbitals where the electrons then circle the atom, circle the nucleus. So he did a lot of his work based on the spectral emission patterns, and we'll talk more about this. This is really pivotal. The fact that these energies, these orbitals, are associated with specific energy levels, and then to jump from level to level, you get a certain energy released or absorbed. And again, this spectroscopy is basically diffraction of light, so it spreads the light out. So Bohr's model actually talks about the fact that these jumps are fixed. Their quantum means a small fixed amount, or a fixed amount, not necessarily small. Photons are specifically small packets of light. So like the particle nature of light. So photons are quantized energy, so it's a fixed amount in this form of electromagnetic radiation. So it doesn't have to be photons of light, but it could be photons of infrared or photons of ultraviolet, but mostly we're going to talk about photons of light here. Also want to talk about the fact that in the electricity, the electron volt is a measure of energy, whereas the voltage was a measure of potential difference. And that'll be important for moving forward, because we're going to use the energies as electron volts moving forward. So, so this is furthermore this is work based on Bohr's model, but it's also, most of this work is attributed to the work of Planck, Max Planck. So he said that the energy of a photon is based on the transition energies of the energy of the initial shell it starts in minus the energy of the shell it ends up in. So if an electron volt is a measure of 1.6 times 10 to the negative 19 joules, he said energy is not continuous, but again, it comes in these discrete packets related to frequency. So Planck wrote the energy of the photon equals E equals Planck's constant times its frequency. So on this, I have this is the energy of the photon, and this is the energy of the photon. So of course, you can often take this and make it equal to this. So back up to here, Planck's constant is 6.63 times 10 to the negative 34th, so E equals HF. Because we have from our last unit the most important equation, C equals wavelength times frequency, we can substitute in for frequency and get C over wavelength, so H equals C over wavelength. So this is actually from your reference table. These are the Bohr model electron diagrams. So in the ground state, in the Bohr model, we'll look at hydrogen first. The ground state has an energy of negative 13.6. The N2, the first excited level, has an energy of 30.4. So if we talk about transitioning from level 2 to level 1, the energy of the photon is the difference in these two levels. So I have 3.4 and 13.6. The difference between them is 10.2. So electrons want to start in their most stable state, their valence state, which is as close to the nucleus as they can until that shell gets full. So if I have one electron, which hydrogen does, and it starts in the ground state, it would take some electricity or some energy to pop it up to the second level. So if I run electricity through a hydrogen light, the electrons might pop up to level 2. Well, it's unstable in level 2, so as soon as it gets to level 2, it then drops back down to level 1 and it emits light. So again, electricity pushes it up to level 2. Light could then be released when it drops down to level 1. And each one of these transitions corresponds with a different energy, thus a different frequency, thus a different wavelength or color of light. So the red light might be a transition from 4 to 3. The green light might be a transition from 5 to 3. The blue light might be a transition from 6 to 5. Each one of these different colors corresponds to a different transition. And as I said, the spectral analysis happens when you diffract light and spread it out, and you get the different colors. So you don't get a continuous Roy G. Biv. Instead, you get specific photons that formulate what colors you see from a different light source. This is a lab that we would have done if we were in school, but this is not the case. So you get two types of spectral patterns. You either get emissions. So on the previous page, I had a light source that was emitting light, and it emits certain colors. So you get this where it's all dark and you get specific colors, and this is the actual hydrogen emission spectrum. Or if you run that light, if you run just white light that has all colors through hydrogen gas, it will absorb certain colors, and those colors again correspond with the photons that get absorbed by that gas. So furthermore, we have, these are the transitions that are specifically for hydrogen. So if I say 6 to 2 is going to give me this bluish, 5 to 2 is going to give me this bluish, 4 to 2 is going to give me this turquoise or light blue, and then 3 to 2 gives me the red. So this is the lowest energy jump, therefore it has the lowest frequency, therefore it has the highest wavelength. You are going to have to reference this, again, from your reference table. Furthermore, we're going to have, part of this is, this is showing the Doppler effect for light. So if we have, so the way that we were able to tell that Doppler light shift is not looking from the light with just our eye, but looking at a light with our spectrometers. So we expected when we looked at hydrogen a certain pattern, or helium had a certain pattern. But as the star got closer to us, every one of these lines shifted over towards the blue end. That's what we call blue shift. And as it went away from us, all these lines moved to the red end. This is red shift. And again, we know that most of the light that's coming to us from space is redshifted light, which is evidence that the universe is indeed expanding. So one more piece of information here. This gives you a pretty good idea of the energy jumps here. So if I pick the 10.2 photon, so again, the electron, the blue electrons in its valence shell, it's got electricity coming in, it bumps up to level 2, and then it drops down and it lets off a photon. So energy comes in, bumps it up to a higher level, it's unstable and it wants to fall back down. So I get a specific amount of energy. That energy that comes in is 10.2, the energy that comes out is 10.2. It has to go to that specific level. If I pump it up to 12.1, it can pop up, and now when it's in level 3, it fell to level 2 and then 2 to 1. So actually, if it goes to 3, it can have 2 photons as it comes down, or it could go straight from 3 to 1. So if I pop this up to 13.2, it's going to pop up to a higher level, and then from that level, it went, oh geez. So it made 3 transitions on the way down. I suspect it's not going to make 3 transitions this time. So it went up a higher level. Nope, so it just made 1. So it's kind of random in where it falls down to. It doesn't fall to the same level every time. If I go back to the notes here, and again, we're looking at the reference table. Each one of these transitions results in a different energy level. So this 2 to 1 is a certain energy level. This 3 to 1 is a certain energy level. This 3 to 2 is a certain energy level. So if I'm up in level 4, I can go 4 to 3, 4 to 2, 4 to 1. And then once I go 4 to 3, I could go 3 to 2, 2 to 1, or 3 to 1 directly. So those are the different transitions it can make. And then once I have that energy, I can say E equals E minus E. So if I was bumped up to level 2, I could then fall back down to 1. So again, the difference the E photon is E equals, subtract those two levels, and I get 10.2 electron volts. And then if I wanted to find the frequency, I can say E equals HF, and this is going to be my E here, and my H is 6.63 times 10 to the negative 34th. I can find the frequency, and furthermore, if I wanted to find the wavelength, I can say frequency equals, speed of light equals frequency times wavelength. So once I found the frequency here, I could take that down to this level here. So we're going to do a lot of problems like this, but hopefully these notes have been helpful.